So just let me hit the record button. So today we continue our warming up period. So you should have, as many of you know, we are still in a warm-up period, so no assignments yet. Let me just share my screen. So here we have the course schedule, as you might know, and we are still in round 0, which is about the components of machine learning. So today I will continue my discussion of the components. In particular, I will give already a preview of how these components are combined in deep learning. But the first actual exercise will be in round 1 on artificial neural networks, and we will release them the latest on 27th of September, and the deadline will be 11th of October. And these deadlines are hard deadlines, so we don't accept any excuses. Yeah, I hope that also many of you found the way to the Slack discussion forum. So if anyone has problems, you can ask now. If you have problems joining Slack, you can ask now on the chat or by voice, or write us an email, please. And I encourage you again, please make use of the discussion forum of the Slack channel. Whenever you have a question, post it there. And whenever you see a question that you can answer, please post an answer. The Slack activity can only be beneficial for you when it comes to grading. So there is no stupid question you can put there on Slack. So please use it. Don't be shy. Okay, any other questions from your side regarding the course organization before I start with a bit material? Okay, there were some questions on the chat regarding the notebooks. So these notebooks, yeah. This actually brings me to the actual content of the lecture today. This course, these rounds, what is most relevant for you in these rounds might be the notebooks. So we have Python notebooks that include coding assignments, and you have to complete coding assignments. You have to complete small chunks of code to achieve some functionality that we ask you to ensure with this code. So let me just walk through some of these notebooks as an example. Yeah, first of all, how can you access them? All these exercises are on the Jupyter Hub server of our department. So how do you find the Jupyter Hub server? So you go to your favorite browser, whatever it is. That's all you need. You need a browser that is connected to the internet. That's all you need for this course. So we go to Jupyter Hub. And then, well, I'm already logged in. So I will stop my server connection. Basically, this Jupyter Hub is a big computer, and every time you log in there, you get your own share of this big computer. So you get a virtual user account on our Jupyter Hub server, on the department Jupyter Hub server, and you can choose between different options for this account that you start up when you connect to the server. And of course, for our course, the option deep learning with Python is most interesting. You will see in your web browser, you will see this deep learning with Python, and I have, of course, the advantage to have also this instructor option. So this gives me a bit of advantage because I have the solutions also. You will not have these instructor options, obviously. So then you start your account on this server. Yeah, and then you will find here this tab assignments. And then you might here have then a button fetch assignments. And currently I have only fetched round 0 assignments. So here you open then round 0. And here it is. So this is the main material for the exercises, these Python notebooks. And the Python notebooks you edit and save regularly. So regularly hit the save button here by connecting to our Jupyter Hub. So you don't need to install Python yourself. You only need a web browser that is connected to the internet or that can connect to our Jupyter Hub server at the department. That's all you need on your computer. Okay. So what are 3 main components of machine learning? Any ideas? Data model loss. Very good. Very good. That's maybe one of the main messages in this whole course, like in any of my machine learning courses. So when you look at, and I always want you, or it would be a good idea whenever you do read Python code, whenever you read Python notebooks or develop Python code, always think about in which component are you currently working. So let's look at this part here. What do you think is this part related to? Are we defining a model here? Are we defining a loss function or data here? Data. So this part here is data. And typically, I would say in more than 90% of cases, the first thing you do is you read in data. So first component, data. Here we get data, and we store data in a particular form or data points. So there are 2 types of properties of data of a data point. So a data point could be a student. So what properties does a student have?
Can have name.
A name, schedule, courses. So the courses or the curriculum or let's say the transcript of a student can be read in easily by connecting to the big database at Aalto. We have a big database where there's every detail of every student. So this is a feature. We call these features. This we can, if you have access, if you have the user rights and given privacy protection, we can read them in. So I can read in for each one of you some information like at least the name, the student ID. So these are features. And this we store typically in an NumPy array called X. So X is typically holding features. There's another type of property of data points. What other type of, like for the student, there could be a higher level fact or a higher level information about a student that we're interested in. What could be of interest to me as a teacher of a course? Well, to me, it could be interesting for each student to know how likely will the student succeed in this course. So we call this type of properties labels. And one might say machine learning or deep learning is all about predicting labels just from the features. So this could be one definition. Informal definition of machine learning or deep learning is about developing software that is able to predict the label value or guess or approximate the label value of any data point just by looking at its features. And we store the labels. So for some data points, we know the labels. So for example, I have asked, we have pedagogical experts at Aalto, and they look at students and they give me their opinion about the label. So this student is very likely to pass the course. This is not so likely to pass the course. So for some data points, I know the label value, and we store this in a NumPy array Y. So again, it's with NumPy arrays. This is maybe the most important variable type, Python variable type for the whole course, NumPy arrays. Try to get a good understanding of NumPy arrays. Okay, so here we have data. What do we do next? So it's then always a good idea to plot the data, to visualize data. So get a feeling. This is, of course, very vague, vague hint to get a feeling for the data, but just try to visualize it somehow. So does any one of you know very simple or basic ways to visualize data? Yeah, plotting, but how? How do you plot data points? So if a data point represents a student, how do I visualize a student? I mean, I can take a picture with my camera of the student, then I have visualized the student. But there's also a lot of digital data. So his or her course history. So if I just look at the file which contains all the data or information about a student, then it's just a sequence of ones and zeros. Or I can use a few numbers like the grades of all the 10 recent courses. So I could use feature values, but yeah, here's very good suggestions. A histogram could be one way to represent data. I could say, I make a histogram of the grades obtained by all the students within the curriculum of the machine learning bachelor course. Or scatter plots. I could plot on the horizontal axis, I could plot the age of the student. On the the vertical axis, I could plot the average grade of a student. Yes, so scatter plot is maybe the most widely and most basic technique for visualizing data. Box plots, another type of visualizing data. But we will not go much more into detail of visualizing data. Just as a hint, whenever you can visualize data points, you know, or you have a technique to draw an image of a data point. And whenever you can draw an image of a data point, a kind of an image that carries some information about the properties of the data point, then you can feed it to a computer vision machine learning system like convolutional neural networks. So visualization techniques could also be interpreted as feature learning techniques. So you use the visualization then as features to characterize a data point, which you then, these features, this visualization, you feed into a convolutional neural network. And maybe most of this course will be about convolutional neural networks, how you train them, how you use them, and how you visualize them. Okay, so now we have data. So the next part would be hypothesis space. Yeah, what is the difference between hypothesis space and model? At least when I use the word hypothesis space, I mean the same as model. A model is a hypothesis space. That's the same thing. And there are also other uses of this word. Yes, exactly. A model is a set of hypotheses. You could also say, maybe what is more intuitive for you is that you say a function, a linear function like this. So I posted on the chat. So you have a linear function of a single variable x is w times x plus b. Then you would say this is a linear model. But what this is actually, what you write down there is a whole set of maps from x to f of x. And this set of maps is obtained by using different weights w and bias or offset terms b. So your intuitive use of the term model is actually not so far away from my, how should I say, more mathematical definition. A model is a set of different hypotheses. And one way to represent such a set of hypotheses is by a parameterized function, like a parameterized linear function. Okay, so how do we use models in machine learning or in deep learning? What's the role of models in deep learning? We train them, yes. So we train them or we fit them to data, yes. So in other words, we search over them. So a model is a set of predictor functions, like here. Where do we have? Yeah, here. Every straight line here in this plot is a different linear map, is a different hypothesis. So the set of all linear functions is a model, a linear model, and we try to find the best one out of it. And what is the best one? So this brings us to the third component. Which hypothesis map should we choose? Here, the green one, the blue one, the purple one. Why? Smallest loss. So here's the third component coming in. We need somehow a tool, a mathematical tool, or a concept that allows us to tell how good or how well does this purple curve fit the data points. And one way to do this is via loss functions. So this is the third component and the final component. Now we have all together. And now we could define machine learning as any method that searches over a set of hypotheses in order to find the hypothesis with the minimum loss. Okay. And that's called, this principle is also called empirical risk minimization. And that's what we do in deep learning mostly. We try to find a predictor map that has the minimum average loss on training data. So for data points for which we know the true label values. And this average loss is also called empirical risk. So empirical risk is average loss on labeled training data. And we want to find the predictor with minimum average loss. So here we also have an example. So let's say we found a predictor with minimum average loss, like this green curve here. It looks a bit like a polynomial. So are we done? Is the machine learning task accomplished? So we found a predictor that fits the training data super well. Exactly, we have to validate. And then we compare validation and training error, and we continue from the beginning. We continue by changing the data. For example, collecting more data points. We continue by changing the model, using smaller or larger models. We continue by changing the loss function. For example, adding a penalty term in order to regularize the method. And then repeat again. We train the model, the new model on training data. We look at the validation error. We compare training with validation error, and we repeat the cycle. And as a deep learning engineer, you just continue the cycle through your work days. So, okay. Any questions at this point about the machine learning or deep learning workflow? So here in this picture, and this is these types of plots you will look a lot at. So this will be maybe your main tool. You can think of it as your Swiss Army knife in deep learning, in the deep learning day-to-day business. You look at such plots and then think about what you should change in the model or in the data. So in this case here, the horizontal axis represents the polynomial degree. So we consider as model here, we consider the set of all polynomial functions with a given maximum degree. So here for this point here, 6, we would consider all predictor functions that are polynomials of degree up to 6. And we then find the best polynomial with degree 6 that has the smallest training error. So we get this point here on the blue curve, and we then validate the resulting degree 6 polynomial. So is this behavior intuitive for you? So why do you think is the validation error going up at some point? Yes, that's overfitting. So overfitting means we have a large model that contains just by accident one polynomial, one very crazy polynomial like this one here, that just by accident or by coincidence perfectly fits the training data, but has a very bad behavior or delivers very poor predictions outside the training data, which are the orange dots here, which is used as a test set. So regarding this notation test set or validation set, so what is similar between test sets and validation sets, both are not used for the training of the model. So a test set is not used for training the weights of a deep net, and the validation set. What makes a test set becoming a validation set is if you use the error on these orange dots, so for example, the mean squared error for all these orange dots, to change the model. So to say, okay, here I overfit, so I should use a smaller polynomial degree. As soon as you use this error outside the training set, the test set becomes a validation set. So you kind of have used up the test set also to somehow train the model or on a higher level. So you not choose within all polynomials of the same degree, but you change the degree, you change a hyperparameter. And as soon as you use this test set error to change something in your model, it's a validation set. And the test set is really only used for a final evaluation, and that you get a figure of merit that you put into the brochure of your machine learning app, but is not used for further development or tuning the model. Then it becomes, if you use the test set error to tune the model or to change the structure of your deep neural network, it's called a validation set. Okay. So when you look at these plots here, what is the best polynomial degree in your opinion? 4, yeah. Why? Why do you think 4 is the best? Yes. Any ideas why 4 is good? Because it has the smallest validation error. Yeah. So that seems reasonable, but it's just polynomial degree 4 here is just the one which has the smallest validation error for this particular data set. And if the data set is small, then basically what you see here is something random. So make sure that you have large enough data sets such that you do not get fooled by just random fluctuations. So when you have very small training or data sets, then this is not reliable. So the validation error might not be reliable. But in this case, it seems there's a consistent trend that above polynomial degree 4, the validation error goes up and overfitting kicks in. Okay. Yes, that was basically. Are there any questions regarding this code demos we have put here, or Shamsi has put in round 0 notebook? Did any one of you already try this out? Okay, yeah, then let's continue. This is my favorite quiz. So I show you a code line and you have to tell me, or I ask you, which component does this belong to? So here, this code line here. So we create a new object from the class logistic regression. Which components do you think are you working on here? The model, yes. So what is the model used by logistic regression? What is the set of hypothesis spaces used by logistic regression? The set of hypotheses, sorry. What type of hypothesis functions are used by logistic regression? Linear, yes, linear functions. Does any one of you know another machine learning method that uses the same model, that also uses linear functions as the hypothesis space? Any guesses? Linear regression, yes. Linear regression uses the same model as logistic regression. And so what's the difference between linear regression and logistic regression? Both use the same model. So in which other components could they differ? Yes, in the loss function, because logistic regression uses which loss? The logistic loss. So in this class not only corresponds to a specific choice for a model, but also for a specific choice for the loss. It's the linear model combined with logistic loss. And they also differ, these methods differ a bit in the type of data. So in logistic regression, we try to predict labels which can take only two different values. So it's binary classification problem. Whereas in linear regression, we try to predict a numeric variable. So which type of loss function do we use for linear regression? Squared error loss, yes. Linear regression by default uses the squared error loss. Okay. So I now suggest we have a short 5-minute break, and then I continue with a particular efficient way to search over large models that is used in deep learning methods, which is based on the notion of gradients. So see you again at 10:35. Yes, and in this break you can also post or dump any questions in the text chat that you might have.